Welcome! My name is Auke Hoekstra and I'm an expert on electric mobility at the Eindhoven University of Technology. In this video I will be going over the main differences between the electric vehicles and conventional vehicles. Because once you get that, everything else sort of falls in place. I do a lot of outreach to mainstream media, and I found that most people really don't understand the basics when it comes to comparing conventional cars with electric cars. And in essence, there are two fundamental characteristics that all cars have that you have to understand. If you do, as I said, everything else falls into place. The first fundamental is energy storage. The second fundamental is the motor. But let's start with the motor. The motor converts potential energy into kinetic energy. You might think that there are many types of motors out there, and if you look at all the articles about the different types of gasoline engines, you might think that's true. But in essence, there's only two types of motors. And this has been true since the beginning of human history. So pay attention, because this is information you can use forever. The first motor is the heat engine, and the second one is the electric engine. In a heat engine, burning releases the potential chemical energy in a fuel. This heat produces expansion, and this in turn drives some mostly rotary motion. This is true for steam engines, Stirling engines, diesel engines, and gasoline engines. The picture shows how a four-stroke engine works. This is basically the modern gasoline engine, and it was invented over 150 years ago. On the first stroke, gasoline is injected into a chamber by opening a valve that is then closed again. On the second stroke, the cylinder moves upwards and the gasoline is compressed. On the third stroke, the energy in the fuel is harvested by igniting it. This is the piece where you get the energy out of the gasoline. The resulting explosion drives the cylinder down, and that produces rotary motion. This is comparable to a bicycle, basically, where pushing down the pedal moves the bicycle forward. On the fourth and final stroke, the energy burned, the gasoline burned, is emitted, and it's all very ingenious, but it has many problems. The entire engine requires hundreds of precisely crafted moving parts, and that makes the engine heavy, expensive. And since all the heat and explosions cause a lot of wear and tear, you need a lot of maintenance, and even then it wears down pretty quickly. It's often the part of the car that is worn down the earliest. The heat engine also wastes a lot of energy. In theory, we could improve the efficiency to about 50%, theory, but that would mean a couple of things. Firstly, the engine would become more expensive. Secondly, it would have to run at almost a constant number of explosions per minute, which is very hard to do in the real world. And finally, the motor should be run at almost maximum power. In practice, even though we've been proving the internal combustion engine for more than 150 years now, a regular car wastes more than 75% of the energy it consumes as heat. And a sports car, like the Bugatti Veyron, wastes more than 95% of the energy if you drive it in regular city traffic. For health and climate change, the biggest problem is the exhaust fumes. The first problem is that they are unhealthy, but the biggest problem is that burning 1 liter of gasoline produces 2.3 kilograms of carbon dioxide gas. Now let's look at the electric engine. It all works completely different. We will dive into all the types of electric engines later, but fundamentally, they all work by using magnetic fields. You might still remember from school that magnets have poles, a north and a south pole. Just like Earth, basically. If you put two magnets together, you will see that opposites attract, right? This is the whole mechanism we're using in electric motors. If we take a coil of wire and make electricity flow through it, the wire gets its own magnetic field. It has become a magnet. And if we place this magnetic coil between two magnets, one side of the coil will be pushed up and the other side will be pushed down, and this makes the coil rotate until it's vertical. At that moment we quickly change the polarity and we go on. That way you can create rotary motion, and what you're seeing on the animation is a simplified direct current motion, current motor in action. The advantages of the electric motor are numerous. It only has one moving part. We call that the rotor, by the way. Therefore, the whole engine can be relatively light, compact, and inexpensive. And since magnetic fields are very gentle, an electric motor can last essentially forever without any maintenance. Energy efficiency, that's really important, can be close to 100%. And you can even win back energy when braking. So theoretically that takes you over 100% if you compare it to the gasoline engine. That's only 25% efficient, as we saw. Because of this, the average electric car is 4 times more efficient than the average conventional car. And if you compare a sports car, the electric car is up to 20 times more efficient. So, oversizing an electric engine doesn't materially reduce efficiency, and the engines are cheap and light. That's one reason why in practice electric vehicles can accelerate much faster. They simply have much bigger engines, and there's no downside to that. For health and climate, the biggest advantage is clear. It can run on renewable energy, and the motor itself has 0 emissions. This sheet sums up all of the different aspects, and it's clear the electric motor is superior in every way. So, why did we end up with a gasoline engine? The answer to that question is energy storage. When you look at motors, electric engine has the upper hand, but if you look at energy storage, the heat engine has the upper hand. Because fuel is a really marvelous way to store energy. Batteries compare very poorly to that. A lead-acid battery from the 1900s stored around 0.01 kilowatt-hour per kilogram. That's more than 1,000 times less than gasoline. No wonder the gasoline engine won. A lead-acid battery at the end of the last millennium was better, at say around 0.035 kilowatt-hour per kilogram, but it's still about 350 times worse. And a nickel metal hydrate battery, NEMH of course, available at the turn of the new millennium, stores about 0.08 kilowatt hours. This is still 150 times less. But then people woke up, primarily because they needed lighter batteries for cell phones, laptops. And now a lithium battery, as produced by Tesla Gigafactory, for example, has about 0.25 kilowatt-hour per kilogram, still 50 times worse. In the near future, say within 10 years, we can expect batteries that store about double that, say 30% worse, 30 times worse. So, theoretically, lithium-air batteries can even hold more energy than gasoline, by the way, but that's very theoretically. So if we take the efficiency of the motor into account, we could have a theoretical situation where actually the batteries are lighter. However, that's a long-term perspective. Now, it's really important that you understand how this works in practice, because in practice the difference becomes much smaller. So imagine we make a car, a conventional car, an electric car, and we want to be able to drive a distance of 500 kilometers, right? So average car, 500 kilometers. In 1900, we would have needed to take 10,000 kilograms with us. A very big elephant in your ordinary car. No wonder the gasoline engine won, right? At the end of the last century, you still had to take a rhinoceros on top of your car, about twice or 3 times as heavy as your whole car. The nickel metal hydrate battery, there he goes, NEMH, turned it into an 800 kilogram bison. But with the advent of the lithium battery, you remember, the one we did because we needed light batteries for smartphones, the 10,000 kilogram elephant turned into a 400 kilogram silverback gorilla. Still a big guy to take with you, but better, right? Within 10 years, it will be about 200 kilograms, or a pig. Now you might say a 200 kilogram pig is still pretty heavy. But if you take the weight of the drivetrain into account, the electric drivetrain is so much lighter that the entire vehicle overall will be lighter from, let's say, 2025. So the whole idea that batteries make electric cars heavy will soon be something of the past, really. The reason I put so much emphasis on weight is not just because it allows you to build lighter and nimbler vehicles, but just as important is the fact that something that is lighter needs less raw materials. And in the end, that means it's probably going to be cheaper. So by making the battery plus the drivetrain lighter for an electric vehicle, we can also make it cheaper. And then all the efficiency advantages come into play. And you also save 25,000 liters of fuel over the lifetime of the car. So, to wrap it up, there are essentially 2 motors for cars. Heat engines to propel the car forward by burning fuel. Electric engines that use much more gentle and efficient magnetic fields. Electric engines are superior in almost every way. They're lighter, smaller, cheaper, require no maintenance, are 4 times more efficient, cause no exhaust, and can run on renewable energy. The problem was that batteries used to be incredibly heavy and expensive, heavier than an elephant. But due to incredible developments in battery technology in the first years of this millennium, the weight of the battery plus the drivetrain will soon be less for an electric vehicle. Taking the fuel savings and the efficiency into account, that means the electric vehicle will be much, much cheaper to own. So, if you look at the fundamentals, the adoption of the electric vehicle is not a question of if, it's only a question of how fast. Thank you.